Okay, guys, we can work on it tomorrow.
Be sure to wear goggles when you're in the lab.
I did so.
Always zero out your balance, and then measure the mass of all things you use. And make sure each marble you use is the same. 4.91. I'm going to put 50 milliliters of each substance in each one of these graduated cylinders. Right now I'm going to put 50 milliliters of water in. And you always measure when measuring the graduated cylinder, put it on a flat surface and measure from the meniscus. At the bottom of the meniscus, it's 50 milliliters. Now I'm going to put 50 milliliters of the soap in here. And I'm going to measure from the meniscus, which is the dip of the top of the soap. Right at the bottom of the meniscus, it is 50 milliliters. Now we're going to measure 50 milliliters of the corn syrup, and we're going to use a funnel this time to make it easier to get this inside. And then always clean out your materials when you're done with them. Always clean your graduated cylinders with test tube brushes and water, and then possibly soap if it's very hard to get out.
We're going to time to see how long it takes the marble to get from the top of this down to the bottom, and it'll measure the viscosity of the liquids. So, ready? 1, 2, 3.
So, temperature stays the same.
Gas law one I can print off what's on here.
Stop.
Was almost instant, which was water. The second one, which was soap, was about 2 seconds. And then the last one was about 17 seconds.
Nate, what is viscosity?
Viscosity is the liquid's resistance to change.
Okay, thank you. Thank you very much.
Go.
Water, as you can see, had the least viscous because it dropped the quickest, and then soap, it was the second because it was only 2.8, and it didn't go as fast as the water. And then the most viscous was the corn syrup because it took 20 seconds to go down.
We're going to measure the density of this marble, and we already have a mass, so now we just need the volume, so we're going to use water displacement. And now we measured it at 20 milliliters of water, so however much it goes up is the volume of this marble. The bottom of the meniscus is at 22 seconds, the volume is 2 milliliters of the marble.
We're going to find the density of this blue marble. The mass, which we already massed, was 4.91 grams, and the volume, which we found through the graduated cylinder, was 2.1 milliliters cubed. To find the density, we would take 4.91 grams divided by 2.1 milliliters cubed, and that comes out to be 2.33 grams over milliliters cubed. But now, since our graduated cylinder only let us go to the 10th place, we have to erase one of these because that's the lowest we can go.
The control of the experiment with the marbles dropping was the graduated cylinder with the water because it had nothing added to it. The same mass of the marbles and the same volume of the marbles, so that wouldn't change anything. And then we used the same amount of all the substances that we dropped it in. The independent variable was the liquids like the soap and the corn syrup that we used. and the dependent was how fast the marbles sank and the viscosity of the liquids.
Okay, this is quantitative and qualitative data over our experiment we just did with the marbles and then the viscosity of all three liquids. Our quantitative is right here, and our quantitative is we had 3 marbles, 3 graduated cylinders. The mass of the marbles was 4.91 for each of the 3 marbles, and then there's 50 milliliters of each liquid. The volume of every single marble was 2 milliliters cubed. The density of each marble was 2.3 grams per milliliters cubed. And then qualitative, well, the water had the least viscosity, the soap was the second most viscous, and then the corn syrup had the most viscosity. And then the water was clear, the soap smelled fresh and was very slippery, and then the corn syrup looked really yellow, and then it smelled like vinegar.
Crystalline has molecules where they're all lined up in a pattern. In amorphous, they're all separated, and they can absorb these. Our countertops are crystalline because they're all aligned in the same pattern. This towel is amorphous because they're all spread out. This crystalline solid has a definite shape and volume, therefore it is a solid.
This is a heating and cooling graph. It starts off solids are at negative 100 degrees Celsius. That's when they freeze and they become a solid. And they also melt at 0 degrees Celsius and they become a liquid. And they're a liquid until they get to 100 degrees Celsius and they start to vaporize, and they either evaporate, which is at the surface of the liquid, or they boil, which is the pressure equalization. And then from there they turn into a gas, and when the particles charge, it's ionization and they turn into a plasma. And going back from that, deionization is from a plasma to a gas, which the particles aren't charged anymore. From a gas to a liquid, it condenses, which is condensation. And then from a liquid to a solid, it freezes. And from a solid to a gas, skipping the liquid state is sublimation. And going backwards from that, gas to a solid, skipping the liquid phase is deposition. And that is when you take away energy, it is exothermic. And when you add energy, it's endothermic.
This is a real-life example of heating and cooling graphs for boiling pasta or macaroni in different parts of the U.S. Now, in the Colorado mountains, which is higher elevation than Iowa, which is normal elevation, and Miami, which is sea level, and in the mountains, it would take shorter time to boil because there's less air pressure, but it would take longer time to heat.
The other thing would be
And then in Iowa, which is normal elevation compared to Miami, which is at sea level, and Colorado, which is in high elevation, it would take normal time to boil and normal time to heat because there's medium amount of air pressure on Iowa, and there's not a ton like there is at Miami or little at Colorado. Now at sea level in Miami, there's way more air pressure than there is in the mountains or at Iowa. So at sea level, it'll take longer time to boil, but a shorter time to heat up because there is more air pressure pushing down on there. We're going to make a physical change with this graduated cylinder full of water and 3 droplets of food coloring. Now I'm going to add 3 droplets of food coloring. 1, 2, 3. Now as you can see, the water is changing color, but it is still water. What?
Here's some ice. We need the baggies.
Although the water has changed color, this is a physical change because we will be able to change this back into its original state.
Although the water is green now due to the green food coloring, it is still a physical change because the water still has the same identity. It is just green. Otherwise, you can just change this back to water and take out food.
Breaking ice cream with rock salt and ice, and the ice lowers the freezing point of the salt, or of the ice cream. The salt lowers the freezing point of the ice. So the ice cream, the heat and the milk and the sugar and the vanilla goes into the ice, and it freezes faster and the ice melts. So the energy is exothermic from the milk and is endothermic for the ice. And that's a real-life example of heating and cooling graphs. And now it's ice cream.
Ice cream!
No. Take me.
Knocked off my head. Like for real.
Oh, almost got 2 for 1. Oh, harder than that. Go. That was good. Give Dakota. Too high. Oh, jeez. Chris is hiding. Get it. Oh, that was good.
Chris, give me as hard as you can. Just like, I want to feel it.
Get it. What?
Nice job, Chris.
Hold on.